This is Module 4 on factor analysis. Covariance is a measure of the joint variability of two random variables. If the greater values of one variable mainly correspond with the greater values of the other variable, and the same holds for the lesser values, then the covariance is positive. In these situations, we can use the correlation coefficient. However, some statistical problems involve more than two and sometimes many independent variables, and therefore the correlation coefficient is not applicable. Further, some problems involve no dependent variable, only a set of independent variables. These situations necessitate analyzing and understanding the underlying covariations among many independent variables in one test. Factor analysis is a statistical method used to describe variability among three or more observed conceptually related variables, and we want to know their underlying structure or how they may be grouped. We call these groupings unobserved variables, factors, latent factors, underlying factors, or components. These are ways of describing the groups of variables determined by a factor analysis output. For example, it is possible that variations in 6 observed variables mainly reflect the variations in 2 unobserved or underlying variables. In other words, these 6 variables can be classified into 2 groups in terms of how they vary. Factor analysis searches for such joint variations in response to unobserved latent variables. The observed variables are modeled as linear combinations of the potential factors, thus error terms. Factor analysis aims to find independent latent variables. It may help to deal with data sets where there are large numbers of observed variables that are thought to reflect a smaller number of underlying or latent variables. It is one of the most commonly used interdependency techniques and is used when the relevant set of variables shows a systematic interdependence, and the objective is to find out the latent factors that create a commonality. These are the topics I will cover. You can see from the graphic on the right what factor analysis attempts to do. The column of boxes on the left represents 25 questionnaire items on the survey. By design, each item should help the researcher assess 5 different traits of respondents. These traits are shown as ovals on the right-hand side of the image. In this case, we input the 25 measures. Factor analysis will tell us if indeed each question item loads on its intended trait. Because several questionnaire items combine to represent a given trait, the traits are commonly referred to as constructs. The items construct the trait for the researcher. Whether an item loads or not on its intended construct will tell us if the instrument, in this case a survey, is valid. In the case that items such as N4 and E3 load onto theoretically the wrong construct, as shown by the green arrows, we grow concerned about the validity of those constructs. In those cases, we may drop or edit the questions from the instrument. Conceptually, this is one use for factor analysis. Later, I will show you what the actual output looks like. We're going to talk about 4 ways to classify factor analyses: saving output, missing data, and underlying assumptions. Anytime you deal with a group of measures, it's important to understand whether they are reflective or formative. Conceptually, a reflective measurement model happens when the indicators of a construct are considered to be caused by that construct. Reflective measures are associated with survey instruments that are meticulously designed by researchers. They are concerned about constructs, as I have mentioned, and each item should replicate one another. In this way, we can make sure our measurement items not only measure the correct thing, but also it's a form of replication, so we can make sure our test results are dependable. So reflective items should all mean the same thing, just worded differently. They are synonymous. So look at diet here. Questions R1, 2, and 3, they all mean exactly the same thing. A formative measurement model happens when the measured variables are considered to be the cause of the latent variable. Formative measures are associated with secondary data sets that a researcher may have access to but did not design, as they would a survey instrument. In this case, the researcher has access to a block of data, and every indicator practically means something unique. But that is not always the case. Sometimes we can design instruments that are formative, as you see here with health. As you can see from these questions, each one has a distinct answer. Because F1, 2, and 3 combine to provide the researcher for an indication of health, they form the health construct. They cause that construct to happen. It's the same as looking at many different pieces of weather data, bringing them together and forming an opinion about what the weather is. So reflective is usually associated with designed survey instruments. Formative is usually associated with a block of data that a researcher has access to. Another way to categorize factor analyses is by the stage of research. For new topics, we will use factor analysis to explore relationships, called exploratory factor analysis. When we've done a few studies and we have an idea as to how the measures will behave, we may be more interested in confirmatory factor analysis. Exploratory factor analysis is a method to explore the underlying structure of a set of observed variables. For example, it is used to discover the factors of formative measures, which concern archival data that was not designed by the researcher. EFA is also used as a crucial step in validation of reflective scales when they are being developed. In other words, we use EFA to validate how well designed and implemented our theoretical survey instrument intended to measure a reflective construct, as I mentioned earlier. In reflective constructs, each question is a replication of the others within the same construct. We want to make sure that each question loads on its intended construct and not the other constructs. A confirmatory factor analysis is a method to verify a factor structure that has already been defined. This is used for subsequent research when we can review previously published work and have a good idea about past empirical results regarding the underlying structure. CFA is almost always used as an advanced tool to validate reflective constructs. As you can see on the right-hand side, exploratory factor analysis, we're considering which item belongs to each factor. On the left-hand side, confirmatory factor analysis, we are imposing on the model that certain items should belong to certain factors. Another way of classifying factor analysis is whether or not we want to inspect components or common factors. Common factor analysis is related to principal component analysis, or PCA, but the two are not identical. The difference relates to how variance among analysis variables is treated. In PCA, only total variance is assumed to make up common variance. In common factor analysis, total variance is partitioned into two types, common and unique. Both methods try to reduce the dimensionality of the data set down to fewer unobserved variables. As the number of variables increases, results from PCA and EFA tend to come closer. Another way to classify is by unrotated or rotated, and there are several ways to rotate factors. In most statistical packages, the factor analysis will produce unrotated or rotated output. The unrotated output maximizes variance accounted for by the first and subsequent factors and forces the factors to be what we call orthogonal. Orthogonal means that after factors are rotated, they are not correlated. We do this when we want a sharp distinction between the factors. This type of data compression that comes with orthogonal rotation comes at the cost of having many items load substantially on more than one factor. On the other hand, rotation serves to make the output more understandable by seeking so-called simple structures. This is a pattern of loadings where each item loads strongly on only one of the factors and much more weakly on the other factors. Rotations can be orthogonal or oblique. Oblique rotations allow for correlations among the factors. So orthogonal means factors do not correlate. Oblique means that factors may correlate. SPSS allows for three types of orthogonal rotation. Varimax is the most common rotation option and maximizes the variance of the squared loadings of a factor on all of the variables in a factor matrix. This has the effect of differentiating the original variables by extracted factor. Each factor will tend to have either large or small loadings of any particular variable. A Varimax solution yields results which make it as easy as possible to identify each variable within a single factor. Another orthogonal approach is the quartermax rotation. This rotation approach minimizes the number of factors needed to explain each variable. Quartermax often generates a general factor on which most variables are loaded to a high or medium degree. Such a factor structure is usually not helpful to the research purpose. Equimax rotation is a compromise between Varimax and quartermax criteria. However, the orthogonality or independence of factors is often an unrealistic assumption. Allowing for factors that are correlated with one another is especially applicable in psychometric research, since attitudes, opinions, and intellectual abilities tend to be correlated, and since it would be unrealistic in many situations to assume otherwise. SPSS allows for two types of oblique rotation. Direct Abelman rotation is the standard oblique method. This will result in higher eigenvalues but diminished interpretability of the factors. Promax rotation is the alternative oblique rotation method. It is computationally faster than the direct Oblin method and therefore is sometimes used for very large data sets. Next, we'll talk about saving output. Here you see the most common depiction of a factor analysis output. You can see we have three factors created by the algorithm. The numbers you see in the table are loadings. Some of the loadings are hidden because the user told the program to cut off at a certain value. Usually that value is 0.4, but you can see from these numbers that the researcher chose a lower number. In a perfect world, we would have perfectly formed factors where each item loaded on only one factor. But as you can see, the second item, stinging, loads on factor 1 and 2 at a minimum threshold loading value of 0.4. This will instigate some concern among the researchers. In addition, irritating, raw, and tender cross-load on factor 1, and given the loading scores, they more appropriately belong to factor 3. In another case, aching cross-loads on factors 2 and 3. By and large, looking at the loading scores, as a researcher, I would only be concerned with stinging because the loading factors are higher on its cross-loaded factor 2 at 0.4. So what can we learn from this analysis? We know what items belong to what factors, but also very importantly, we learn about what factors exist, and we can label them. We can use what we know about these items to label factor 1, burning and stinging. And we can think about labeling factor 2 based on the characteristics that loaded on it, sharp and stabbing. With factor 3, we can think about how to label it based on aching, irritating, raw, sensitive, tender, and sore. In this way, we have analyzed a number of independent variables, and we have learned about their underlying structure. But what is not included in this analysis is any dependent variable. Following an exploratory factor analysis, factor scores may be computed and used in subsequent analyses. Factor scores are composite variables which provide information about an individual's placement on the factor. There are several ways for accomplishing this. Number 1, for each factor, sum the scores of the individual measures. Number 2, sum only individual measure scores, meeting a threshold for loading on a factor. Number 3, for each factor, sum the standardized values. This can be applied to all factor items, or only those meeting a loading threshold. Number 4, sum items weighted by their factor loading. Again, this can be applied to all factor items, or only those meeting a loading threshold. So we can summarize each factor by using these scores, and there are different methods for doing this. Missing data is a frequent problem for researchers conducting factor analysis. The SPSS factor procedure allows users to select one of the following options, which are methods for dealing with missing data. First is listwise deletion. In listwise deletion, a record or row is dropped from the analysis because it has a missing value in at least one of the specified variables. For example, you can have 500 variables and 1 million records. If only one variable has a missing value, the entire record is omitted from the analysis, although the variable remains. The analysis is only run on cases which have a complete set of data, so the listwise option will cause the record to be omitted for the entire procedure. Second, pairwise deletion occurs when the statistical procedure sometimes uses records or rows that contain missing data. The procedure includes a particular variable in an operation whenever it is not missing, but does exclude it when it is missing. So the pairwise deletion option means that within the factor analysis procedure, sometimes the record will be omitted and sometimes it will not. Third, mean substitution. This approach calls for replacing each missing value with the item mean. It is very problematic because it will directly suppress effect sizes. Mean substitution should only be used when there are very few missing values. The shortcomings of these methods are well known. A better approach is single or multiple imputation, although these methods require additional analyses and can be tedious. Next, we'll talk about the underlying assumptions of factor analysis. Since factor analysis is based on a matrix of correlations, both procedures are based on the same assumptions. You want at least interval or ratio data. The data needs to be asymptotically or approximately normal. The data needs to have linear relationships among them. You don't want redundant measures. For example, you don't want the exact same calculations to appear twice in your set of variables. But we do want the measures to be conceptually related in some way, and we should expect some intercorrelation among them. A good rule of thumb is that you want at least a Pearson's R correlation coefficient of 0.3. And now I'll walk you through the Module 4 dataset activity. The dataset is provided in this link. Click it, and assuming SPSS is installed, the file will open. The dataset provides 30 items, 17 of them belonging in a scale called life and 13 questions in a scale called confidence. We've already collected the data, and as is common with factor analysis, we want to run multiple analyses and compare results. First, we want to run the analysis and allow the eigenvalues to determine the number of factors. Second, we want to restrict the number of factors to 2 because our researcher designed the survey instrument as 2 constructs comprised of the items that I mentioned. So we go to our data set to run the factor analysis, click Analyze, Dimension Reduction, Factor. We could select each item by pressing Control and then clicking one item at a time, but I've already been through this step and I know that it's a lot faster just to select items 1 through 30. To do this, you click on the first one, press down Shift, and click on the last one, and it will select all of them. So pressing Control will allow you to select each individual item. Pressing Shift allows you to quickly select all of them. Move them over, and these are the variables that will be included in our factor analysis. Click on Descriptives. Under Statistics, we want Initial Solution, which is already pre-selected. Under Correlation Matrix, click on KMO and Bartlett's test of sphericity. These are 2 tests that let us know if there is enough intercorrelation among the variables in the analysis, an important assumption of factor analysis. Press Continue. Click on the Extraction box. Keep the selection of Principal Components, which is the default method of extraction. Under Analyze, make sure Correlation Matrix is selected. And in Display, Unrotated Factor Solution. And in this test, we are going to allow eigenvalues to determine the number of factors. To see eigenvalues graphically, click on Scree-plot. We do want to extract based on eigenvalue, and a common threshold is an eigenvalue of 1. We also want to stick with the number of 25 for maximum iterations for convergence. Press Continue. Click on the rotation box. Under Method, we select the most common orthogonal approach, which is Varimax. Under Display, make sure Rotated Solution is selected. Again, maximum iterations for convergence, stick with 25. Press Continue. If we wanted to save factor scores, as described earlier, we would click on Scores, but we're not going to do that. Next, click on Options. We want to select Exclude Cases Listwise. Under Coefficient Display Format, we want to sort by size and suppress small coefficients. We will use the cutoff value of 0.40, also suggested earlier. Displaying our coefficients in this way will make our output a whole lot more readable. Press Continue and press OK. First, we need to know if the data is amenable to factor analysis. Click on the KMO and Bartlett's test, the output table. Since the KMO measure is greater than 0.80, it supports the use of factor analysis on this data. Similarly, the Bartlett's tests of sphericity is used to evaluate whether the underlying correlation matrix is suitable for the factor analysis. It tests the hypothesis that the matrix is an identity matrix, a matrix in which all coefficients not in the diagonal are zeros. In this analysis, the p-value for the Bartlett's test is 0.000. This finding supports proceeding with the analysis. The next table shows the communalities for each of the 30 items evaluated. The column labeled Initial presents 1.000 for each of the 30 variables. This simply indicates the number kept in the diagonal of the correlation matrix, always the case when using principal components analysis. In the column labeled Extraction, there is a listing of communalities for each item. Later I will show you that 4 factors were established by the analysis. Again, that was based on eigenvalues. Therefore, the extraction value of 0.492 for energy level represents the amount of variance in that variable that is accounted for by the 4 derived factors. To get the exact amount of variance explained by the factors, you would have to square that value. So that would be 0.49 squared, which would be 0.24. In other words, 24% of the variance in energy level is accounted for by the 4 factors. The next table contains information needed relative to general characteristics of the factors, both before and after the rotation. SPSS uses the term components because we chose principal components analysis as the extraction method. So you see that all potential factors or components are listed because we have 30 variables. We have 30 potential components or parts. And on the right side of the table, we see only variance explained data for the 4 derived factors. For these 4 factors, we have initial eigenvalues, percent variance accounted for by each factor, and the cumulative percent of variance accounted for by the factors. The factors are also sorted by total percentage of variance explained in all the variables. Note that the first 4 factors, as we set in the procedure properties, have eigenvalues greater than 1. That was the cutoff that we set. And the 4 factors are sorted by eigenvalue. Note that when you compare unrotated and rotated factor structures, the amount of variance explained is closer in the rotated factors than unrotated. This indicates that variance is more equally distributed among the rotated factors than unrotated. We're explaining the same amount of total variance in all of the variables, with 57% accounted for by the 4 factors, but the factors that we have constructed by rotating are doing so more equitably. You can learn more about how these factors were selected by clicking on the scree plot. The scree plot provides a graphic representation of the relative values of eigenvalues. Because eigenvalues often are the key criteria for determining the number of factors to be rotated, this can be useful because it provides a basis for identifying a logical breaking point between eigenvalues. And you see we selected 4 because this line passes 1 right here between factors 4 and 5. You can see this numerically on the total variance explained table right here. And you can see that these values are based on unrotated results. Click on the component matrix. This table presents loadings for the 4 factors extracted. As usual, the first factor is a generalized factor on which all variables load. The other factors have only a few loadings in the moderate range and none above 0.5. Typically, no attempt is made to derive conceptual interpretations of these unrotated factors. So this is a table that is analogous to the unrotated factor matrix. We will not use it in our research. For that, click on Rotated Component Matrix. This table shows the rotated component matrix. It contains the rotated solution that we will interpret. In this portion, the 4 factors with eigenvalues greater than 1 are rotated, and the final solution is displayed. These rotated factors are to be conceptually interpreted. Note that the items are listed by the strength of loading, not by the order in which they were entered. In SPSS, this is done by checking Sorted by Size under Option. And remember, we suppressed all values less than 0.4. At this point, it is helpful to inspect the items that load on each component and label the components. You can see there are cross-loadings, but by and large, it's a clean factorial structure. There is one problem with this, however, and that is that the researcher designed the instrument into 2 dimensions, not 4. So let's go rerun the analysis and impose only 2 factors and see what happens. Again, go back to Analyze, Dimension Reduction, Factor. Click on Extraction. We want to bypass selecting the number of factors based on eigenvalue. Click on Fixed Number of Factors, and the number of factors to extract is 2. Press Continue and press OK. We see that KMO and Bartlett's tests are both satisfactory. Move to Rotated Component Matrix and you see we now have just 2 factors. It does appear that there is cross-loading, but as the researcher we can also define what is cross-loading and what is not. We could say that our cutoff is 0.45 instead of 0.40. Let's modify our analysis to take that into account. Click on Analyze, Dimension Reduction, Factor. Go to Options and change how we want to suppress small coefficients. Press 0.45, OK. And our rotated component matrix looks a lot cleaner because we have changed our threshold for what is cross-loading and what is not. Our only concern at this point is one item which cross-loads on the 2 factors. Otherwise, we have an entirely clean 2-factor structure. Our researcher may also want to inspect whether or not specific items indeed loaded on the factor they were intended to load. If not, we would need to edit the items or delete them from future consideration. I hope you found this video to be informative. Thank you.